Francke, and welcome to Lab 5 for Physics 2, Magnetic Braking and Faraday. Starting with the introduction, the purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare the computational predictions with the observed data. This is all done to ultimately help understand Faraday's law and to better understand it by seeing it in action. Some concepts that you have to know beforehand are the Biot-Savart law, Faraday's law, Newton's law, and the results or conclusion of the experiment. The times found for the actual experiment were 1.25 seconds, and those for the computational model were 1.14 seconds. Moving on to data, the length of the tube was 0.3 meters, the width was 0.006 meters, the inner radius of it was 0.0244 meters, the outer radius was 0.03 meters. Mu was 2.05, and the mass of the magnet was 0.025 kilograms, and the average times was 1.25 seconds. On the right, you can see the graph or the table of trial number and change of time, and the average found of all of these trials at the bottom, which is roughly 1.25 seconds. Starting with the glow script, for step 1, part 1, the data that was collected was filled into variables in the data. For step 1, part 2, we had to find mu of the magnet and calculate. I had to calculate it again because the results in lab 3 turned out to be incorrect. For step 2, we had to make a function to find the magnetic field of a bar magnet. In step 3, we had to make a function to find the magnetic flux. For step 4, we had to find the current in the ring. And for steps 5 and 6, we had to edit lines to compute the magnetic field at each ring. For step 7, part 1, we had to find the force of gravity along the y-axis. And for step 7, part 2, we had to add up the net force. And finally, in step 8, we had to update the magnetic's velocity and position. So looking at the velocity versus time graphs that were found from the data, the graph on the left is the graph with the ideal mu that had to be changed because the result from lab 3 was found to be incorrect. The mu that was found again through trial and error was around 4.7. On the right is the graph of velocity versus time from the lab 3 result of mu. Which was found to be incorrect. As you can see, the graph is very different from the ideal graph. That mu was around 2.05. So in conclusion, from this lab experiment, we've learned to study Faraday's law, both through computational and experimental methods that allow us to better understand what is going on. As a subproduct of this experiment, we also learned more about magnetic flux and induced current. The actual experiment result was about 1.25 seconds, and the one found in the computational method of the glow script was 1.15 seconds. For sources of error, unfortunately, due to human error or some other error, the value of mu that was found in lab 3 was not accurate and had to be roughly found again using the computational method while guessing and checking. This was done to match the mu value to the ideal graph. Some of the questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So, according to Ohm's law, this would increase the value for current immensely, and it would take even longer for the magnet to make it through the tube if the experiment was done again according to the procedures. Next question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes or slots cut into the tube, that model would have less rings, or N would be smaller, and would result in a reduction in induced current alongside reduced magnetic force. This would ultimately cause the time it takes for the magnet to fall through the tube in the experiment to decrease.